Thank you. All right. So, just glancing through the reflections quickly, feels like a lot of us were not that prepared, but just glancing through, what did a lot of us also not do?
Study.
We didn't study. How did we think it was going to go if we didn't study?
We're going to have test anxiety.
Frustration.
Oh, test anxiety, frustration there. I do want to point out this one person said they felt prepared for the test because I've been practicing my check your understandings. The implication there being that they didn't wait till just before the test. They've been doing the check your understandings along the way. And so that sounds like a pretty good thing to me. I really want to emphasize that it doesn't come down to just being smart or anything like that. There's a lot of us that at least had a good bit of evidence of understanding, but I think as Finney just said, hey, if you're not studying, then you're going to be more stressed out. You're going to have test anxiety and not know if you're prepared or not. So please remember that in moving forward, that we really need to make sure we are staying on top of check your understanding questions. Check yourself, like I've given you those answers. Now, today we're not going to get super far into the unit, so that is the good news. And so I don't have any check your understanding questions for you today, but I will have some tomorrow. Now, I will also say this, Ms. Granberry and I worked this summer, we met up and talked about how we want to organize things, and so we've actually restructured some of Unit 2 from how we've done it in the past, so I'm going to have to make some new check your understanding questions. So I'm going to try to stay on top of it, but things did change a little bit, so we're going to have to be aware of that. The last thing I want to mention is I think I saw it on one or two people's tests in this class yesterday, and then it came out, it was way more prominent in fourth block. But I got to ask you, have you ever heard me say the word qualitative in this class? No. Do you know what qualitative is very similar to, though? See, it's not quantitative, so it would be similar to categorical. It's related. The reason I bring that up is because I had way too many students writing down that one of the types of data was qualitative. And yet, it's weird. We haven't talked about the word qualitative once in class. In the same question, when I asked about the type of sampling, I had a few people write down cluster sampling. You know what you've never heard me talk about in class? Never heard the word cluster sampling. You know what also wasn't on our proficiency scales? Them words, right? Cluster sampling or qualitative. Say again, sir?
Sounds like somebody cheated.
It sounds like almost like someone cheated, except not very well. It's hard, guys, to cheat on my test. I cannot emphasize that enough.
You're going to cheat. Don't use words you never use.
Right, like, if we're writing down words you've never heard in class, that should be problematic. If there's terms that are not on the proficiency scale, that might be problematic, right? Guys, listen, I want you to learn. And so when it comes to my assessments, it's going to be clear if you have studied or not. I don't know how that happens, but I will say this, like the question that I'm referring to, so I just happened to glance at or notice it on that one. Question I'm referring to is from a stats set of assessment and practice questions that I have, but I I rewrote the question specifically for what we have done in this class. Every question on that test was built off of the proficiency scale. There's not going to be things outside of what we've studied. We're also, at this point, going to have to make sure we put all purses and backpacks at the front of the room on test day, because that means that we are doing things that we shouldn't do. Technically, we're not even supposed to have smartwatches in class. That's one of those things that I'm supposed to collect and send to the front office. Okay, but those are going to have to 100% be gone as well. So I just want you to be aware of that moving forward. Just a problem I solved. Anyways, so we got 2 Hero Mondays. Dean's going next week. Walter's going the week after that. They volunteered. From there, on a happier note, Rihanna's going to rejoice. Coriana's going to rejoice because we're no longer doing statistics. We're getting into traditional mathematics, the Algebra 2 side of Algebra 2. And so here's the thing, and this is what I want y'all to hear. The way that Ms. Granberry and I restructured Algebra 2 is to help build stronger foundations from the beginning. Trust us, we'll get you there, okay? Trust us on the way we've restructured it. 1, 2, everything in the last unit, none of it's gonna impact your ability to engage in this unit. So, that's the good news. Hopefully, through that first unit, you have started to learn how my class operates, you've started to learn how we need to work together, right? How we need to actively collaborate, things like that. So I need us using our brain, engaging in things that we have. You with me, Walter, instead of on your iPad? Oh, look, you got a week and a half.
Yeah, go ahead, do it. Sorry.
Okay, you got a week and a half, but not in class. Okay, so we're going, can you let Annalise in, Dee Dee? We are going to be engaging in more traditional Algebra 2, and what we did in the past is not going to hurt you at all. However, don't forget, it's not just about a test. What percent of your overall grade is that test? 20%. Your DYUs is what percent? No, DYUs, 10%. Active collaboration? No, not 70%. Active collaboration was 10%. Your proficiency scales, guys, that's 50%. You have an exam at the end of each 9 weeks, right? And that's 10%, right? So your proficiency scales are 50%. So let's say there's a skill that I didn't see evidence of understanding of on the test or on any of the DYUs or conversations in class. You can still come in before school, maybe right after school if you talk with me ahead of time, and we can sit down and talk through things, and then you come in again and show me that you understand that idea so I can mark it off. It doesn't matter when you learn it, it matters that you learn it. I will actually include some of the stats questions on future assessments, not as a part of the grade for that assessment, but as a chance for you to show proficiency, okay? So those are things to think about. Today we're going to first talk about, we're going to work on a task of to use or not to use algebra. And so the focus with this is mathematical representations. The reason why I'm doing this first before we get into what's called an arithmetic sequence and geometric sequences, you are most commonly used to one type of mathematical representation and one type only. Well, what are those? Okay, so that is slope-intercept form of a line, but are both of those slope-intercept forms of a line? No, what are those?
Equation.
Those are equations, okay? So what about this? What is that? It's not an expression, good thought though.
No, exponent. No, it's not exponent.
So what is this saying? That 3x minus 4 and 7 are what? Equal. Is this saying that those two things are equal?
No.
No? What's that saying?
They're greater.
No.
This is saying
Yeah, that 8 is greater than that.
2x plus 7 is
Greater than that equation.
less than 8. Okay? So they're showing, so I'm going to talk about two things there to make sure this is clear. But notice it's not showing they are equal, it's showing that they are
Different.
okay? So if, let's say it this way, these two things are not equal. Does anyone know a prefix that we have in the English language that means not? Nothing? Have we studied prefixes in our English classes at all? So un is a common one. So they would be unequal, okay? That's a good thought. There's another prefix that's pretty similar to un, in. So this is called an inequality. Because what does that prefix in mean? Not. So not equal. Not equality, right? So I just want to break that down a little bit before we get going. Someone mentioned expression. That's an expression. Why is that an expression?
Because it doesn't have a
It's not solved because we haven't solved a single thing. There's no what? There's no equal sign and there's no, what did we have in the last one? There's no inequality sign, right? Less than, greater than, less than or equal to, greater than or equal to. Those are inequality signs. So this is just an expression. This is what we're used to doing most of math with, okay? And this falls under a branch of math called algebra, right? When we talk about expressions, equations, inequalities, that's all algebraic representations. But algebra is just one way to represent mathematical ideas, okay? And a lot of times, algebra is the end goal. Literally, we're in algebra 2, right? Algebra is the end goal. And if we try to jump to algebra too fast, we don't fully understand what those equations, those inequalities, and those expressions really mean. So what's another way that you've represented mathematical ideas in your classes? What else have you created besides equations? I'm going to say one of them, and you're like, oh. What did you do with...
Graphs.
Oh, did you ever make a graph out of that? Oh yeah, so can you make graphs?
Yes.
That's another mathematical representation, a graphical representation, okay? Anything else we've ever done with our graphs? There are things that you've used in your science classes as well. It helps you organize your information. Say it again. Ah, tables. You've done XY tables, right? You can do more than just 2 variables though. So tables are really, really helpful for organizing our information. The most common mathematical representation, and the reason why most people don't recognize math in their everyday life, is a verbal representation. What do I mean by verbal? Speaking, right? So what do you use when you speak? You're using... You guys, in order to speak, what do I have to use? Your mouth. Thank you. But what's coming out of my mouth?
Vocal.
What is it? Words. Yes, vocal, that's the sound, but like words, right? When we say verbal, we're saying that we're using our words, okay? And then finally, this one is more, I will say, for geometry, but also sometimes it helps us just understand and see things. Now, it's pictorial because it's an adjective form, but it's a pictorial representation. What do you think I mean by that, though?
Picture.
Big picture, right? Like sometimes you can draw out a picture to make sense out of things. Now, what I want to emphasize before we start this unit, and I need you to hear me clearly on, is this. We're going to work towards algebra, but that's not the starting point. Graphs, tables, pictures, and words can significantly impact your ability to understand the algebra. And so, we're going to do a lot of algebra. But I also want you to think about other ways to tackle mathematical problems. When you go to take the ACT, most of y'all are juniors, some of y'all, a couple of us are sophomores, but when you go to take the ACT, you're mostly going to see stuff like this. Not to this level of depth. We're going to look at this task in a second, but we're going to see stuff like this, and that's what throws a lot of us off, because we're like, oh my goodness. I'm not used to using words. I'm used to being given an equation or given a graph or given a table. But we need to learn how to engage in verbal representations and make sense out of what's going on. So here's our task, right? So you're going to have 2 different problems, and I'm going to give them separated by a good bit. So we're not doing 3, we're only doing 2. I dropped one of them off. So you have to solve problems in at least how many ways? 2. In at least 2 ways. One of those ways is going to be what? Algebra, and the other is...
Words.
You could use words. What else could you use?
Graphs, tables.
You could use a graph, you could use a table. I don't care which one you use, but I want us to start to see how we can use other representations. By the way, do you have to start with the algebra? No. Could you start with a graph or start with a table to make sense out of what's happening? In fact, I would highly recommend that. Okay. So then we're going to use our vertical surfaces to present our solution methods, look around the room, and we're going to discuss advantages and disadvantages of each method. So, you have 3 heads in every single group. I want you actively collaborating and talking and making sense out of these problems so that you can figure out what's going on. So I'm going to leave the first question up here. let's, trying to think. I'm gonna leave it up here. The Jackson 4s, try to share that right side of the board so that everyone can clearly see this. So here's what's happening. The local swimming pool offers two, actually I'll write it up here, and Jax, just don't write over this. So local swimming pool offers two possible ways to pay for your summer time at the pool. You can either do a seasonal pass of $240, and I think that's Roy. So Roy chooses, so a $240 pass. By the way, how many times is he going to pay for that pass? But it's a seasonal pass, so for that summer, how many times is he going to pay for that? Just one time, okay? So $240 seasonal pass. And by the way, I need eyes up here, because I got a lot of us not looking up here, and then we're going to be like, Mr. Kitty, I don't know what's going on. Correct, eyes up here. Dalton, eyes up here. Thank you. All right, so $240 pass, and plus $10 every trip, right, or entrance. I'm going to call it a trip. So every time he goes to that pool, he's going to pay $10. $240 is only once. $10 is every time. Okay, but then Joel, or that's Joel, I should say, it could be Joel, but Joel, we'll go with that, is choosing the second option of $25 per entrance. Or per trip. Now, I want to point this out. Initially, is gonna cost more for? Roy, right? Roy's got to pony up how much money at the beginning? $240. How much is Joel ponying up at the beginning? Not even $25. If he doesn't ever go, how much does Joel pay? $0, right? But every trip, Joel is having to spend how much? $25. Whereas Roy's only going to have to spend $10. So eventually, depending on how many trips you go, who's going to spend more money? Joel's going to end up spending more money. But here's what's actually happening. Throughout the season, they went to the pool every single time together, right? So if Joel goes once, Roy goes once. If Joel goes twice, Roy goes twice, okay? And at the end of the season, Roy and Joel were surprised to find they paid the same amount to enter the pool. How many times did each of them go to the pool during that season? So, went together. And paid the same. So what's the question here? How many times did they go?
So they both spent $240. No?
Well, here's the thing. First off, and I just want to point this out, Joel couldn't ever spend $240. If Joel went 10 times, how much has he spent? He spent $250. But remember, Roy spent $240 one time, but if he goes 10 times, that's $100, right? So it can't be that, right? So what I want you to think about is work with your small group, put your heads together, think about what representation you want to use. We got to figure out how many times do they go together. We also need to figure out how much each of them spent. That would, in that case, right? So I didn't tell you how much they spent. I just told you they went the same number of times together and they ended up spending the same amount of money. So let's get up to our vertical surfaces. Let's tackle this problem and let's figure out how many times they went to the pool. Alright, so Jax and Fours, they use this space up here together.
Move in.
Oh, you could have just gone once you finished your reflection, but yes, go. In this conversation. So, right here, okay? So first things first, I just want to point this out. Someone's like, but Mr. Kinney, I could write an equation pretty easily. That's cool. Because legitimately, we're dealing, what kind of function are we dealing with here? Kind of. The function. Like, look over there, those graphs that someone created. What is that? What shape do you see there? Someone said it. Thank you. Guys, we see a line on that graph. So what type of functions are we talking about? Thank you. Linear. Hey guys, We got lines on those graphs, right? So we're talking about a linear. Do you know when you first started studying linear functions? It's not quite 6. 7th?
Yeah.
8th is when you really started getting into linear, and then you did lines in your geometry class, and then you did lines in your algebra 1 class. So I've been doing lines for a long time. So guys, when I am trying to get y'all to do these tables and do these graphs, it's not as much about the linear functions as what we're going to go into later. Okay, hopefully we're comfy with linear. So I'm starting with a type of function that you have done a lot with to build strong foundations for when we get into exponential and quadratic and cubic and quartic and quintic functions, okay? And square root functions and logarithmic functions. Like that's what we're going to go into eventually, all right? So we want to build strong foundations here. All right, so please hear me and please pay attention to this. First things first, if I've got a rate of change, and I know things are changing, which things were changing. For Joel, what was changing every trip? How much was he paying extra? $25. For Roy, how much was he paying extra every trip?
$10.
Okay, so when I see a change going on, a change with a pattern, if you know how to create the equation right away, awesome, create that equation. But what's a strategy, Dean, that you started with really quickly that didn't take a whole lot of effort?
The table.
That table was pretty fast. Like, Dean got there pretty quick. Now, I'm going to point out a couple of things that I really like about this table that I would highly recommend, and that we see over here, right? Because, Malia, we got a little off at first until we started drawing these lines. Hey guys, drawing a horizontal line across makes it really easy to see what goes together, okay? All right, so when we make tables, please, so first off, change with a pattern. And I don't see the equation, make a table. Okay? Tables are great for patterns and change, okay? Once again, and this is something you will want to write down later. What are tables great for? Patterns and change, okay? Tables are great for patterns and change. When we see clearly what is being repeatedly added or something like that, table's a great option. This shows up all the time on the ACT, and students are like, Mr. Kinney, I don't know what to do. And maybe they don't recognize the linear function. Can you quickly make a table and figure out what's going to happen? Yes, Mr. Kinney. Great. I know, I got you, Walter. I heard you. Okay, so here's what I want to point out. Okay, there's two actual things over here. So first things first, right here, okay? I want you to see, because again, some of us saw the equation. Some of us wrote 25t like this right away, or the 240 plus 10t right away. That's great. But I want you to look at this table. When I was talking with Malia's group, Malia was talking about the fact, the way I got this 50 was I took my number of trips and multiplied it by 25. I took my number of trips 3 and I multiplied it by 25. 4 multiplied it by
25.
Okay, so notice how that 25 does not change whatsoever. So you know what number has to be in my equation or in my expression?
25.
The 25's got to be there, right? But this thing that's changing, what's something we can use in math to represent something that changes? Starts with a V. A variable. Guys, the reason why, and so there's a couple of things I want y'all to understand is this is a variable because does anyone know what we call this type of variable that we're putting into an expression? No, not an exponent. Sometimes, but exponents we're going to come to later. That variable that we're putting into the equation. Into. I'm putting it into the equation. I am putting it in the input is changing. We're going to talk a lot about inputs and outputs this year. And so here's a vocabulary term I need you to hold on to. Okay? The variable, right? We're using a variable there because what is happening? The input is changing. That's a variable. Remember we talked about categorical and quantitative variables, or data, because the responses could what? Change, right? That input is changing, it's a variable, okay? So I'm going to come back to that in a second, so hold on to that. Over here, notice Roy was a little bit different, because Roy wasn't just 25, 2 times 25, 3 times 25. Ooh, sorry, I forgot something really important. That's just the variable. Most of the time, when I talk to students even in Algebra 2, and I just say, why is it 25t? Like, I don't know. I mean, it just is. But Ms. Kinney, it is 25t. I don't disagree with that. But why is it 25t? I need you to hold on to this, because, Finney, you brought up slope-intercept form of a line, right? I want us to understand what that equation is actually saying, not just, hey, this is the equation. Understand what it means. So, what's happening between that 25 and that t? Yeah, guys, we write 25t, right, just like that, right next to each other all the time, without thinking through the fact that that's 25 times t. But that 25 times t is wicked important. Because what are we doing with that 25?
Multiplying.
Look here, what are we doing with that 25? We're repeatedly adding. And we talked about it over here. Hey guys, what y'all say a faster way to add was? Or to repeatedly add? Oh, guys, it's not just 25t, it's 25 times t. So we're multiplying because multiplication is repeated what?
Adding. Addition.
Yeah, repeated adding or repeated addition. Because multiplication is repeated, yeah, faster. That's a great way to say it. It is repeated addition. So guys, if you see repeated addition, you know what you're going to end up doing? You're going to end up multiplying. But I need you to hold on to that, because you're like, Mr. Kinney, I don't need this. Like, I already know how to do a linear. But what about when it becomes repeated multiplication or repeated division? So I'm taking something you know, and I'm going to build you up to something more. And I need you to hold on to this. That multiplication, because that multiplication is repeated addition. So the variable, because the input is changing. We're multiplying here, because multiplication is repeated addition. Now, when I come over to here, okay, notice we talked here, what's repeatedly happening in this table? For Roy. So it's going up by 10. Use better language than just going up by 10. Oh, thank you, right? Like, we need to recognize it's repeatedly what? Added by 10. So, Carly, if I see repeated addition, what am I going to end up doing? I'm going to multiply. So, look. When I talked to this group, we talked about the fact that Roy spent $240 from the beginning. But if I want to go to 5 trips and go straight to 5 trips, he added 10 how many times? 5 times. If I want to go to 10 trips, he added 10 how many times? If I want to go to 12 trips. And so, hey, because this input is changing, what's that going to become? It's going to become a, because that input is changing, it's going to become a, say it then. Oh, it's a variable. Hey guys, I need us to all understand this. I need us to come together on this. We need to recognize that input is changing, so it's going to become a variable. Okay? Now, what I want to now emphasize, so by the way, could we take that table all the way to 16 trips and get our total there? Now, there was something I forgot to do. I just want to point this out really quickly. Notice this group did something really efficient. Did they go by 10 trips every time? All of a sudden here they went by 5s. But hey, if to go from 290 to 340 is plus, so if 5 trips is $50, well, if 1 trip is $10, what's 5 trips? 50. See how they sped that up? If 1 trip is $25, what's 5 trips? $125. Hey guys, if you find that pattern, that change, you don't have to go by 10 every time. You can speed it up, right? So you could even say, hey, I'm going to go by 10, right? So we went by 5s here. But if I went by 10 trips, how much is Roy going to spend over 10 trips? So remember, 100, right? So 1 trip was $10, 10 trips is $100. And so what was it for Roy, by the way? 10 trips for Roy, no, for Joel. 10 trips for Joel would be 250. Notice how when I multiply this by 10, I gotta multiply that by 10. So we can speed our stuff up once we find those patterns. So that's what I want to emphasize as well. That's why I was trying to get these tables. So guys, there's a lot here about tables that I need us to recognize. I've highlighted it. There's a lot here about variables I need us to recognize. But now I'm going to talk about what's up at the front. So I need us to turn our attention up front. I'm going to turn the camera that way so we can see it. Okay, so I'd like you to join around here. All right. I didn't say sit down. I just said join around here. All right.
Why everybody sit down, bro?
That's what I'm saying.
That's what I'm saying.
Hey, dog. Or just ignore it, whatever. Okay, right here. All right. So there's two things I want to talk about right here. And this is something I need you to hold on to. This is something that I will be expecting you to learn and understand long term. Someone, I don't remember who it was, when I was up here, they're like, I think it was Finney. You were like, Mr. Kinney, isn't that supposed to be a Y? Does anyone know what this notation is called, though?
Why?
No, okay, so the traditional is f of x because f stands for function. This is known as a function notation. This is important because if I just put a y here and I didn't look at the problem, do you know who that's referring to? But if I put j of x here, for however many trips, we're talking about Joel. For however many trips here, I'm talking about Roy. That makes things way more efficient. Function notation is a better way to show inputs and outputs. So a function notation shows inputs and outputs, right? For everybody, my inputs was the number of trips, but then we had the outputs of Joel's price and Roy's price. Notice I do want to point out, have I really even talked about the 16 trips that it took them to get to the same amount of money yet? No. This wasn't designed to just get to that 16. This was designed, Jal, you with me? Okay? This was designed to help us understand mathematical representations and see how these things go together. So, please understand that function notation is important. It shows inputs and outputs. Now notice, when I say j of 5, what did that 5 take the place of? That x, right? So where there's an x over here, what's going to go in for that x? 5, right? That x has now become a 5. Notice now, I'm not just saying y equals 125. I am saying at 5 trips, Joel has spent. So notice this shows my input and my output. The function notation is a way better notation when we start talking about functions. Okay? Mr. Anderson's over here going, yep, 100%, right? Like, that is a reality. I'm trying to get you all to see these things. So this function notation is great. Whereas if I was to look at Roy, that 5 has taken the place of the x. So 10 times 5 plus 240. 50 plus 240 is 290. So at 5 trips, Roy has spent $290. So I want us to see that function notation. Wicked, wicked important, okay? Using function notation. Victoria, you with me? Sure? Helps us look at what we're talking about. That function notation helps us see our inputs and outputs together. A lot of algebra is based on inputs and outputs, not just one or the other. Now, you'll notice like this table was actually made later for a different group. This group right here did not make a table to start. They made the equation. And then I talked with them about going from that equation to these functions, right? And then they use these functions to make a graph. But could you have used this function to also make a table of inputs and outputs? Right? That input of 5 maps to an output of 290 and 125. So this is why we need to be careful though, right? This 5 is supposed to be a 125 and this 5 is supposed to be a 290 and those aren't even lined up. That's why I was talking about those lines earlier. When I make a table, I would put lines in there. Okay? But I want y'all to see this. Here's Joel. Now I can't really make a smooth curve through here because here's the thing. Can Joel go 2.5 trips to the pool? No. We're actually going to talk about this a little bit later. That's the difference between a sequence and a function. But here's Roy. It's a little off because we don't have a full coordinate plane like with the Mars. I know you were asking about that earlier, Dean. But if everything was the right spacing, do you know where this is intersecting? At how many trips? 16 trips. And how much money? $400. Don't look at the fact that it's a little off. I want y'all to notice though, did it matter whether I made a table or made a graph? No. For those of us who are like, I just want the equation, notice the graph is telling the same story. And did you know those graphing calculators can actually find that point of intersection for you without you having to do all of this algebra? So I'm going to teach you how to do that. There's lots of ways to approach mathematical problems. It doesn't just have to be an equation. So, please understand, making a table, that's great for finding patterns. Variables, right? That's when the input is changing or when the output is changing. We multiply because there's repeated addition. Now, here is where I actually need us to pay attention to algebra. There are common algebra mistakes right here that almost everybody made and I need us to learn from. So algebra mistakes. Right here. Hey guys, you can't take 10 from 25x. We also can't take 10 from 10x. What are you actually saying? No, they're not trying to divide there. They're trying to subtract. But let me point this out because I need y'all to see this and learn why this is a mistake. When we say 10x, what do we really mean by 10x? It's repeated something. It's repeated what? Addition. And so we can say that it's repeatedly adding 10, or I can say it's repeatedly adding x how many times? 10 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Hey, can I take away 10 from that? No. 10 what? What am I taking away? No. I'm trying to make a 0, but what am I taking away? 10 what? Say again? 10 trips. Yeah, I'm trying to take away 10 trips. That's not the number 10, that's $10. What do I need to take away? I need to take away 10 trips. What do I need to show that? How do I show 10 trips?
10 with a T.
10 with a T? So, because there's an X right there, I would need to use an X, but if I make it a T, that works. Because now, I'm taking away X how many times? 10 times. That's what's really happening. If you don't put that variable, you are mathematically making huge mistakes. I got to take away 10 x's. Notice what's x minus x?
X.
Yeah, you're right. No. X minus x? You were right originally. 0. What's x minus x?
0.
For anyone's like, how in the world is that true? What would be 5 minus 5?
0.
10 minus 10?
0.
11 minus 11? Right? So x minus x is 0, okay? So notice, I've got to take away x 10 times. That's important. Now 10t minus 10t, it doesn't just slash out. What did we just make? We made a 0. If I take 10 t's that I've added together and I take away 10 more t's, I just made a 0. Same thing over here. If I have 25 trips and I only take away $10, that's not the same thing. But if I take away 10 trips, how many trips am I left with? 15 trips. And those 15 trips are equal to how much money? $240. Like, we need to understand what's actually happening here. We're saying that 15 trips is $240. Now, here's the next mistake. Look at what was circled here. Anyone see the problem? And this would be t's, right? What's the problem here?
They said 50.
Let me ask you this. So x minus x is 0. What's t divided by t?
0. 1.
That's 1. 5 divided by 5 is? 17 divided by 17? Okay, so if I take t and divide it by t, I get 1. If I take 15t and divide it by 15t, what do I get? So right here, we just made 1 on the right-hand side equals 16 divided by t. Is that what I wanted? what should we have divided by? Not 15t.
16. 10.
I want just this t. I want just the t. So what do I need to divide by?
15.
I need to divide by 15. Guys, dividing by 15t is not the right case. When you're adding and subtracting, you need the t to make those zeros. But right here, what is 15 divided by 15?
1.
And 1 times t is t. That gives me my number of trips. What's 240 divided by 15? Okay. So, a couple of things here. When adding and subtracting, keep the variable. And don't just make that a simple rule, but please understand the idea right here. Like we're trying to subtract out those trips. We're trying to subtract out the x's to make a 0. But what about when multiplying and dividing? Do I divide by the variable? No. When multiplying or dividing, don't include the variable. Again, I want to point this out. What's happening between the 15 and the t? They're being what? Multiplied. And how do I undo multiplication? No.
Divide.
Divide. I'm trying to undo that multiplication, so I need to divide by 15, not 15t, just 15. Guys, that gives us our number of trips on its own. These are common mistakes that will impact your ability to be successful later. This is not one of the things that's like, oh, Mr. Kinney's wasting our time. I'm telling you this because I've seen it time and time and time again when students make mistakes with these details that it causes them problems later. So I have a Frere model that I want you to take some notes on for that problem. Okay. So guys, please note on this Frere model, it's a little bit different than normal. I have set up the different quadrants for the different representations. Okay? Hey, I need y'all to listen. I've set up the different quadrants for the different representations so that you can write about tabular and graphical representations in one space, right? Maybe making the notes where I talked about, hey, put those lines across in the table to help keep us organized. The table helps us stay organized. Tables, right? Great with finding patterns. Under algebraic representations, I would probably make a note about the variable when the input is changing, and also make that note about multiplication, right? Like when do we multiply? Well, multiplication is repeated addition. Those are things we want to keep in mind about algebra. Function notation. That's a great thing for algebra. There's a couple of other small things I'll point out later, but I would at least have that information down. One thing I will note, pictorial and verbal, the big thing I would say there is convert it to a table or to a graph or to an equation. Pictures are a great place to start, but try to make it into a table, a graph, or an equation. That's what I would point out there. That'll help you a lot on the ACT. Please let me know if you need help figuring out things to clarify as you work around. Again, there's a couple of things I would add. Make sure you have some of those key terms up there. So entry fees is the task we just did. And hold off on that, I'm going to talk about that. Okay, so entry fees was that task if you want to write down that problem, but there is something I do want to point out, and so just leave that alone for a second. So So mostly focus on the top right, bottom left, and bottom right.
What do we put on bottom left?
Bottom left?
What you just call me?
Alright guys, we should hopefully have filled out a ton of stuff on that prayer model by now. You've had a while to write. One thing I want to be careful about, because I just saw this and I realized I need to make this more clear. Don't forget, that T still comes down here with that 15. Because here's the thing. How many T's are we adding right here?
25.
25 of them. So what are we doing right here? We are taking away how many T's? 10. So if I had 25 T's and I only take away 10 T's, how many T's am I left with? 15 trips. So please make sure when you add and subtract, you're adding and subtracting, you keep the variable even in the sum or the difference, okay? Then we only divide by 15 to get the number of trips on its own. But here's what I want to point out when it comes to that top left section. When we talk about all representations, what have you noticed that's in both graphs and tables and in the algebra? There's two words we've used on every single representation.
Variables and variables.
But we talked about inputs and outputs. Which type of variables?
Input.
Well, there's a type of variable.
Independent.
Independent and dependent. Guys, when we talk about all representations, we are talking about input and output pairs. Okay? When we talk about all representations, it doesn't matter how we're representing it, we're talking about inputs and outputs, or independent and dependent. Okay? So we're talking about inputs and outputs. And even though this graph, does it visually look the same as these tables that we created?
No.
No? But are they telling different stories or the same stories? So notice that input of 2 trips had $50 for Joel. This input of 2 trips had how much for Joel? $50, right? So those two representations, the same inputs map to the same outputs. Right here, when we talk about this graph, the input of 5 trips for Joel had how much money for the output? 125. Is that the same thing we saw in the graph and in the table? Yes? So, relations, and I'm only going to call it a relation for now, because I haven't clarified relation versus function, but relations are the general term. So relations are equivalent. I need you to hold on to this, okay? Relations are equivalent if the same input maps to what? Remember I talked about same what?
Output.
Same output. That word map in math just means that they go together, right? This input of 5 mapped to what output? 125, right? Inputs mapping to outputs. So relations are equivalent if the same input maps to the same output, even if the representations are what? Different. Relations and functions are all about inputs and outputs. It's about patterns and rates of change. And so it doesn't matter if you start with a graph or a table or an equation, because they'll be what? Equivalent. The same inputs are mapping to the same outputs. So your job is to find those inputs and outputs. Your job is to find those inputs and outputs. No, I could have just as easily taken these. Man, these are so far off. Don't kill me. I could have taken that input of 4 mapping to 100, and that's exactly what I see on the graph. The graph, the table, and the equation are all telling the same story. Does that make some sense? Okay.
So Fx is function notation.
Yeah, f of x is function notation. Notice the x would be my input, f of x would be my output. That's why j of 5 trips for Joel is $125. Right, so it tells me a lot. Function notation tells me more than just y equals. It tells me who or what the thing goes with. Okay? Please on that all representations, make that note of inputs and outputs. If you have inputs mapping to outputs, you have a relation. We will mostly study special type of relations called functions. But if inputs and outputs map, you have a relation. Okay? Everybody have the information they need? I see Jess writing a little bit. It looks like Victoria still is. That's perfectly fine. Huh? You just saying you want it on your own paper?
You never got my bill.
Oh, your bell ringer. I thought you were saying you were writing on your own paper. Thank you. Oh yeah, because you went to the bathroom and I forgot to look at it.
No, I just,
Alright,
no, because I was telling you.
I'm about to erase some of this so that we can continue. Alright, Mr. Anderson, can you grab the growing dots from the back? Yeah, maybe pass that out. Okay.
Sure.
Yeah, and then after that, pass out the proficiency scales as well.
It's
Just one page, the growing dots, yep. Okay, so Mr. Anderson is passing out the sheet. Yo, we have 8 minutes. Wait. Okay. Now I have to talk about it.
We could just listen to it.
Or I could teach.
No, because I couldn't
Nothing, Janice.
I be missing it, I'll tell you.
Right, I'm trying to get into some.
I'm trying to get in the club.
I'm trying to get in the club. I can't listen
Excuse
to
me,
that.
then we gotta stop talking overall if we're trying to get into clubs or whatever.
You're the main one.
Who
I
said
ain't even trying to be funny. I'm like, I'm so for real.
Walter. Not yet. And no, actually. Ivan, if we're trying to say we're listening to announcements, y'all can't be talking. Yes. I would just go ahead and flip it over. No. So you just, here, just turn the whole side. That would be smart. Hey guys, don't panic. As soon as it ends, we're gonna talk. Guys, I'm just gonna teach through the announcements if we're gonna be this loud. Jess. Jess, sorry, Brianna.
On the Hillcrest Theater Instagram and other Hillcrest social media, or stop by the Radio Street on Tuesday. If you are interested in applying for the Chick-fil-A Career Academy, sign the QR codes around the school to apply. Applications are due Friday, September 5th. Hey Pat, do you enjoy soccer? Are you interested in joining the team or just getting more information? Please complete the interest sign-up form for boys and girls that can be found on the library windows, office windows, outside of room 400, and outside of room 0.
If you leadership leaders, remember that your taxable t-shirts are due Friday, September 5th. If you like to purchase a t-shirt or you will be leadership students for the interview. EP leadership students will have a very important meeting this Thursday, September 6th.
You said it's 3.
No, it should only be 2. I accidentally gave you this one.
There'll be 2 in the club.
Yeah, there's the A and B is the front and back, and the C is on the homepage.
I just realized.
Says on the end.
He said my name, I was like, you know.
Can I see my old ones?
Or not.
After the bell. All right, so let's talk through just a couple of details with this one. So I just want to get us started. Notice what we're focusing on still is mathematical representations. Like that is actively asked for in this task. That is also what we just did. What we're about to learn about, nope, already did equivalence, I'm skipping that. What we're about to focus on is actually the 2B, arithmetic and geometric sequences. So talking about rates of change, what a sequence is, what a function notation, slope, multiplication, and then all of these things. So I actually talked about some stuff already that I didn't intend to. Tomorrow, when we come together, we are going to look at this growing dots task. Mark the way you see this pattern growing in the sequence of figures given. So like mark it up, see where you see the growth going on. There's a few different ways to talk about it. And assuming the pattern continues in the same way, how many dots are there at 3 minutes? Most importantly is part 3, how many in 100 minutes? Find a pattern, use mathematical representations to help you start to answer this. So go ahead, in the next 2 minutes, do what you can. I'll tell you when we have a minute left of class and you can pack it in. So talk with each other, help each other. You'll see differences in ideas, but still equivalence, and that's important.